Hello and welcome to my channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. In inferential statistics, we don't have all the data from a population or process, so we perform statistical tests on a sample or samples of data. The two main methods of inferential statistics are hypothesis testing and confidence intervals. And there are four statistical concepts which are central to inferential statistics. P, the p-value, alpha, the level of significance, critical value, and test statistic. In the book, there are individual articles on each of these four concepts, and there are individual videos on them as well. This is the fourth. Next to be developed is a video on how all these four concepts interrelate and work together, which is something I think is lacking in most books and videos. As usual in the book and in these videos, we'll start with a list of keys to understanding, or KTUs, and then we'll go into detailed explanations of each key. The first key to understanding is a statistic is a numerical property calculated from sample data. A test statistic is one which has an associated probability distribution. The second KTU is there are four commonly used test statistics: Z, T, F, and chi-square. They are used in a variety of tests in inferential statistics. Key to understanding number 3 states, a higher value for the test statistic tells us that the sample is likely to be more accurate as a representative of the population or process as a whole. The fourth KTU is the calculated value for a test statistic is a point on the horizontal axis of the test statistics distribution. It marks the boundary for P, which is the probability of an alpha error. The fifth and final key to understanding says, if the test statistic is greater than or equal to the critical value, and this is statistically identical to P is less than or equal to alpha, we conclude that there is a statistically significant difference, change, or effect. That is, we reject the null hypothesis. And here on one page are the 5 keys to understanding the concept of test statistic. You may want to pause the video and read them all together. A statistic distills the information contained in the multiple data values of a sample into a single number which is used to describe that sample. The mean and the standard deviation are 2 examples of statistics. A test statistic has the additional property of being associated with a probability distribution or a family of such distributions. Given a value for the test statistic, we can use the distribution to tell us how likely that value is. It gives us a point probability. For example, this is the probability distribution for the test statistic Z. It happens to be the standard normal distribution. That is, the normal distribution with a mean of 0 and a standard deviation of 1. For any value of Z, we can find the point probability of that value. For example, we can visually see that the point probability of Z equals 0 is about 0.4, and the point probability of Z equals 1 or negative 1 is around 0.3. But point probabilities of test statistics are not all that useful. Much more important are cumulative probabilities, the probabilities of ranges of values. Cumulative probabilities are plotted as areas under the curve of the probability distribution of a test statistic. If we have a value for Z, say Z equals 1.645, we can plot it on the horizontal axis, the Z-axis, of the probability distribution of z. The cumulative probability of the range of values from z rightward to infinity is calculated as the integral, the area under the curve from z rightward. Here we see that if z equals 1.645, then the cumulative probability is 5%. Similarly, if we knew that the cumulative probability was 5%, the distribution would tell us that z must equal 1.645. That's what happens when we select a value for alpha, the significance level. In inferential statistics, we don't have all the data for a population or process, so we take a sample or samples of data and use their properties to estimate or infer properties for the population or process as a whole. The person performing the test in inferential statistics selects a value for alpha, the level of significance. Alpha is the highest p-value which they will tolerate and still call the test results statistically significant. Here, alpha equals 5% has been selected. We're using z as our test statistic, and this is a right-tailed test. So 5% is plotted as a shaded area under the right tail of the curve of the z distribution. The probability distribution tells us that the boundary of this shaded area occurs at the point z equals 1.645. This boundary for alpha is called the critical value. Let's move on to key to understanding number 2. There are 4 commonly used test statistics: z, t, f, and chi-square. They are used in a variety of tests in inferential statistics, that is, statistical analyses involving samples of data. This video is an overview of the concept of test statistic. In the book, there are individual articles on each of these test statistics and each of their tests, and I plan to do individual videos as well. Check the videos page on the book's website, statisticsfromaz.com, for the latest status of available and planned videos. Z is unique among the 4 test statistics in having only one probability distribution, the standard normal distribution. This is the bell-shaped curve, the normal distribution, which has a mean of 0 and a standard deviation of 1. The other 3 test statistics each have an infinite number of probability distributions, one for each value or combination of values of degrees of freedom. For data which is normally distributed, z can be used to determine the probability of exceeding or of being less than a specified value of x. As will be shown in the video on proportions, z can be used to give a confidence interval of a population or process proportion. Z can also be used in a hypothesis test of the difference in proportions between 2 populations. With means, you're better off using the test statistic t. Use z only when you know the population or process standard deviation, which most of the time you don't, or if you have a very good estimate of it. And use z only when the sample size is large enough. Some say a sample size of n equals 30 is large enough. Others say n equals 100. For large sample sizes, there is little difference between the z and the t distributions. There is a different t distribution for each value of n, the sample size. These distributions are shaped like the familiar bell-shaped curve of the normal distribution, but they are wider. As n grows larger, the t distributions grow narrower, converging to the z distribution. The standard deviation of a t distribution is smaller for larger samples, reflecting the greater accuracy which one would expect in larger samples. Consequently, t self-adjusts for sample sizes. When t is used, small sample sizes produce larger margin of errors than large sample sizes. That is why t should be used instead of z for problems involving means when the sample size is small. For sure when n is less than 30, although some experts say when n is less than 100. There are 3 different t-tests. The one sample t-test compares the sample mean to a specified mean. The specified mean could be a target mean, a historical mean, or anything else. In a two-sample t-test, the means of samples from two different populations or processes are compared. In a paired t-test, the sample consists of a pair of numbers from each individual test subject. For example, let's say we are evaluating the effect of a training program on the performance of 20 employees. We would measure each employee's performance before and after they took the training. So for each employee, we would have a pair of before and after measurements. F is the test statistic used for comparing variances from two populations or processes. As such, it is analogous to the two-sample t-test, which does a similar thing with means. Roughly equal variance is a prerequisite for being able to conduct a number of statistical tests and analyses, including ANOVA and the two-sample t-test. F is also used behind the scenes in the calculations performed by ANOVA. F is calculated simply as the ratio of the two variances. The larger variance is always on top as the numerator, the smaller is the denominator. The shape of the F distributions varies with the degrees of freedom of the two samples. Degrees of freedom here is equal to sample size minus 1. In these graphs, the critical value is the point on the horizontal axis at the boundary of the shaded area representing alpha. Most distributions can handle either continuous data, like the normal distribution, or discrete/count data, like the binomial or the Poisson distributions. But depending on the test, chi-square can handle either. There are 3 chi-square tests. Individual videos are planned for each. Whereas the F test compares two sample variances and is analogous to the two-sample t-test, the chi-square test for the variance compares a sample variance to a specified variance. As such, it is analogous to the one-sample t-test. The chi-square test for goodness of fit compares multiple predicted numbers to actual data. For example, we might predict what percentage of our restaurant customers would come in for each day of the week. We would later compare those with the actual numbers. The chi-square test would tell us whether there is a statistically significant difference, that is, whether our predictive model is good. The chi-square test for independence can tell us whether there is an association or a statistically significant difference between two categorical variables. For example, whether or not gender influences ice cream flavor preference. There is a different chi-square distribution for each value of degrees of freedom, which is the sample size minus 1, and the shapes change. Also notice that the mean of a chi-square distribution is equal to the degrees of freedom for that distribution. Key to understanding number 3 states, a higher value for the test statistic tells us that the sample is likely to more accurately represent the population or process as a whole. Here we're defining more accurate as having a lower probability of an alpha error, that is a false positive. That is the error of concluding that there is a statistically significant difference when in reality there is not. The seesaw or teeter-totter on the left illustrates this for the test statistic t, and the one on the right shows the converse. A low value for t corresponds to a higher probability of an alpha error. There are different formulas for the different test statistics and their different tests. This is the formula for t for the two-sample t-test. In the numerator, we have the difference between two sample means. A larger difference makes the test statistic larger. That stands to reason that a larger difference between the means makes it more likely that the difference is statistically significant. The sample size is also in the numerator, although its influence is somewhat mitigated by the square root. A larger sample size would magnify the effect of any difference between the mean. In the denominator, we have a standard deviation term. If the variation in the data is large, the accuracy of any conclusion drawn from the data would tend to be lessened. So a large standard deviation in the sample or samples results in a smaller value for the test statistic. KTU number 4 says, the calculated value for a test statistic is a point on the horizontal axis of the test statistics distribution. It marks the boundary for P, the probability of an alpha error. Earlier, we showed a formula for calculating the value of the test statistic T from sample data. The formulas vary by test statistic and test. In this illustration, we are using the Z test statistic. The sample data was used to calculate the value Z equals 1.2. We plot this on the horizontal Z-axis. That value marks the boundary for the area under the curve, which represents the p-value. P is the probability of an alpha error. If Z equals 1.2, then T must be 11.5%, and vice versa. The p-value and the value for the test statistic contain the same information. We can get either one from the other, given the probabilities provided by the probability distribution. Noting the graph of alpha below, Z is larger. 1.645 is to the right of 1.2. This makes the area under the curve smaller. That is why a larger value for the test statistics result in a smaller p-value. Conversely, a smaller value for the test statistic moves the boundary to the left, resulting in a larger p-value, a larger probability of alpha error. KTU number 5 says, if the test statistic value is greater than or equal to the critical value, and this is statistically identical to p being less than or equal to alpha, we conclude that there is a statistically significant difference change or effect. That is, we reject the null hypothesis. The picture shows a close-up of the right tail of the t-distribution. The shaded area represents alpha, the significance level. The shaded area is sometimes called the rejection region. Its boundary is marked by the value of t called the critical value, t critical. Let's say that we have selected alpha to be 5%. Then the white area to the left has an area of 95%. This is called the fail to reject region. And the hatched area to the right of the test statistic value t represents p. P is the probability of an alpha error. In this picture, we show t is larger than t critical, so it is to the right of t critical. This makes the area bounded by t smaller. So p is shown by the hatched area, and it's less than alpha, shown by the shaded area. So p fits entirely within the rejection region of alpha. This means that we reject the null hypothesis, and we conclude that any difference change or effect observed in the sample data is statistically significant. Note how this illustrates that p being less than alpha is statistically identical to t being greater than t critical. Here we've added a third column to illustrate the opposite case. T is less than t critical, so it is to the left of t critical. The hatched area representing the p-value begins at t and extends to the right. With t being smaller and farther to the left, this hatched area for p must be larger. P is greater than alpha, the shaded area. P extends beyond the rejection region and into the fail to reject region. So we fail to reject the null hypothesis, and we conclude that any difference, change, or effect observed in the sample data is not statistically significant. Note how this illustrates that p being less than t critical is statistically identical to p being greater than alpha. Okay, that's it for our clarification of this confusing concept. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book. if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website, statisticsfromatoz.com, has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some interesting things there, like a statistics tip of the week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.